Today, let's try to solve this week Q4 problem. This is a medium problem, although it's a Q4, so it's not that hard of the problem, in my opinion. Basically, in this problem, you are given an integer n, and you're also given an integer x. We want to know how many unique integer of n1, n2, all the way to nk, which means just any unique subset of integers, and all that for example, this is a unique subset of integers, but this is not a unique subset of integers because two kind of repeat. So this one is also a unique subset of integers. Now that we know that we want some unique subset of integers, so here, after we obtain this valid unique subset of integers, and we want to apply the power of x to every integer inside this subset. For example, this one will be x, and this one will be x, and then this one will be x. And we want to know that if the sum of this thing is equal to n. Now we know n and we know x. For example, a subset which is 1 and 3, and then n is 10 and x is 2, right? So we have this subset and we can apply 1 to the power of 2, and then this 3 to the power of 2, and then this 3 to the power of 2 is just 9, and 1 to the power of 2 is 1. 1 plus 9 is 10, so 10 is exactly what we want here. So that's why this is a valid. That's why we have 1, but there's no another way to do it. So for the second example, there's a subset. This is a valid subset because there's no repeated numbers in here. So 4 to the power of 1 is just 4. So 4 is what we want. And there's another way to do it, so it's 3 and 1. And then this is just 3 to the power of 1, 1 to the power of 1, and the sum of this is 4 as well. So we have two subsets could be our potential answer. So in this case, we don't have to return this thing and return this thing. We just have to return the number of it. And that's pretty much all of the problem. And let's see how can we actually solve it. Okay, so to solve this problem, let's first think the problem recursively. So what I mean by recursively is that let's just define this fi, freemin. So this recursive function just means that we want to return the number of ways to make up remain if we start at I. By I mean just the number inside a subsequence that we are interested in, or a subset. Obviously, the answer that we want is f1 because the subset that we consider, the smallest positive numbers that we can consider is 1, and the remain at the beginning is n. So we basically want to know that starting from 1, how many ways that we can make up these numbers n, which will be our final answer. But how are we going to achieve it? So let's think about what options do we have. If we start at I, then basically we only have two options, right? If you think about it, like it's like a general theme of all these subsequent or subset problems. You basically have two options. One is to include I. The other one is to ignore I. Basically, we have these two options, right? There is no third option. You either include that in our subset or you ignore that in our subset. So basically what I'm trying to say is if we have to think all of the possibilities, then we just do this 1 and do this 2 recursively, and we just make the sum of this thing, and we just know the total of everything because this is the all possibilities that we can consider, and we have considered that, and we just take the sum of these two, and it will be the answer that we want. So now let's think about how to do them recursively. Well, this one is easy, right? If we just ignore I, it means that we don't want to include I inside the subset. So in here, there is just I plus 1 to look at the next element, and the remain will just remain unchanged, right? Because we ignore it, so the remain will not change, that's obvious. If we include I, the things is a little bit more complicated. So the first argument is also easy, because yeah, we still have to consider the next element. But in here, so what is the remain? Because we know that everything put inside the subset will have to apply the power of x. Basically here, it just remain minus I to the power of x. Then we have a new remain for the next element in the subsequent. So basically what I'm trying to say, we just sum these two, just add these two together, and that will be the answer that we want. Of course, there is some base case that is very obvious as well, when the remain is kind of negative, or I is greater than n. So the remain is negative, that's obvious, because when it is negative, there's no way to bring it back to positive, because all we do here is just keep subtracting it. So if it is negative, it will remain negative, but we want it to make up the exact element, so we want remain equals to 0. If it is less than 0, then there is no way that there is an answer, so we just return 0. If I is greater than n, so let's think about it. If it is this thing, actually, because we look from the small value to the big value, because we I plus 1 every time, so if this I to the power of x is greater than n, and then I plus 1 to the x is also greater than n, or 2, or 3, so it doesn't matter. So once we hit something like I to the power of x is greater than n, then we just return 0, because there's no way that there is an answer after this. If it is remain is 0, on the other hand, it is a valid solution, and just return 1. So that's basically the gist of the solution. Let's see what is the code implementation. Okay, at the beginning, we just declare a mob that we're going to use, because the answer is going to be big, so the total answer need to be in the modular of this thing. And then we're gonna make the cache of our recursive function to make DP, basically. As I mentioned, we're going to declare a recursive function, and the first argument is I, and the second argument is remain, which I stands for the current number of the subsequence, whether to include it or not, and remain is the remain numbers that we have to make up with. If the remain is 0, it means that we have already reached the answer, so it is a valid solution, so we just return 1. If I is greater than n, or remain is less than 0, or just either power of x is greater than remain, so it's a base case. So if we hit the base case, so there's no possible solution after that, so we just return 0. And in the line 10, so this is the first scenario that if we include I, then for the first argument, we're just I plus 1. For the second argument, because we included I, and because I is already in the subset, and everything in the subset need to apply the power of x, so we need to do remain minus I to the power of the x. That is our new remain, pass that to our next recursive function. On line 11, there's the possibility that we just ignore I. So if we just ignore I, we don't include that in our subset. So we just do I plus 1, and the remain will remain unchanged, no pun intended. Eventually, we will just add two possibilities, because on line 10 and line 11, if you think about it, that's all the possibilities that we can consider. So if we consider 2, it means that we have covered all the cases. So we just add them 2 together, then we will have the total count that we want, and we have to apply the total answer to our module. So that's why we have to mock this thing and return that at the end. At the beginning, we start considering the smaller positives in a subset, which could be 1. It doesn't mean that we will include 1, because we will decide whether to include it or not in line 10 and 11. So it just means that we start considering from 1. And then n is initial remaining numbers that we want to make up with. That's basically all to our solution. Let's try to run this. Okay, accepted. I hope you enjoy or find this video helpful, and I will see you next time. Bye bye.